here. Okay, so now, thank you, Giorgio, for these nice words. I will quickly give an overview, and thank you everybody for being here. Thank you the committee for having accepted my thesis. Thank you all to my friends and family who might be watching. I will give a quick overview of what we have seen. I will not go into much details. And I will talk a little bit about everything we did in the last 4 years. And
sorry, Santiago, just a very quick point. We're not seeing slides.
Yes,
I don't
yes.
know. Okay,
I
okay.
will share, yeah. So I will share screen now. So I guess now you're seeing this, right?
Yes, perfect. Thanks.
Okay, perfect. Okay, I will just jump in. As George was saying, thank you very much, everybody, for being here. And if there's some problem with the audio, just tell me. Or also, if you have some question, just please go ahead, interrupt me. And yeah, okay. So this is the table of contents, a very, very quick overview. I will first talk about the general motivation of the topic. What is the problem we were trying to solve? Then I will present our methodology, which is based on algebra valued models. And then I will basically present two generalizations or two ways of modifying these models and obtaining new models, which is playing around with negation, and then also modifying the interpretation map, which will give us 0.5, which are the LP valued models. And then I will just give some conclusions, some directions for future work, and that's it. Okay, very, very basically, the general question we were trying to answer is, why do we do mathematics such as we do? Why do we do mathematics classically, right? So why do we accept intrinsically certain logical assumptions within our mathematical theories? And one way of asking this question could be that you say, how much of standard mathematics can you recover in a non-classical set theory, right? Or as here, are mathematical theories such as set theory compatible with non-classical frameworks, right? And in my thesis specifically, we have focused on the family of para-consistent logics. So we wanted to construct para-consistent set theories which have interesting models. And the problem with doing set theory or with doing non-classical mathematics is that normally you don't have natural models for these theories, right? And then you have other set theories, which is more probably the most accepted non-classical set theory, which is interjonistic set theory. This is just an example, right? So interjonistic and constructive set theory have gained a lot of recognition in the last years. You have a lot of research in it. You can think about descriptive set theory, etc., right? And so AST, which is short for interjonistic set theory, began to gain more recognition since interesting models were developed for it. So this is a hypothesis that I have, right? If this is somewhere in the literature and somebody knows this, I would be very grateful for this, for the recommendation, because I have not found it, but I think this is a valid argument. So interjonistic set theory gained more recognition due to its model theoretic advances. And one example, which is quite curious, is, for instance, that it's consistent with interjonistic set theory that the real numbers are uncountable and at the same time subcountable. Subcountable here means that you have a function that goes from some subset of the natural numbers into this set X, right? So in classical set theory, countability and subcountability are equivalent. But here it breaks down, right? And then you will ask yourself, but where's this model? Where can I find like these real numbers? Or where can I find this representation of these real numbers? And actually you can build a Heiting valued model, which validates the axiom of interjonistic set theory. And in this construction, the real numbers are subcountable. So this is just one example of saying that you can find interesting models for non-classical set theories. And that through these models, the set theories have gained more recognition in a certain way. Or rather, if you would ask like a classical set theorist, why don't you do non-classical analysis? I don't know. I think you would say that you don't have expressive models to do it. So the main goal of my thesis was precisely to provide this non-classical set theories, or in my case, paraconsistent set theories, with interesting model constructions. Okay? So in a certain way, what has been done for intuitionistic and constructive set theory, we wanted to extend this analysis to paraconsistent set theories. In principle, I think the analysis can be extended to any kind of non-classical set theory, so any family of non-classical logics. So the choice of paraconsistent set theory was kind of not arbitrary, but it was, I think it's extendable to other non-classical logics. Okay? So this is the starting point. This is the question we were trying to answer. How much standard mathematics, how much set theory can we recover in a paraconsistent set theory? And actually, there was a book which was published, I think it's a few weeks ago, by Zach Weber, and which is called Inconsistent Mathematics, which basically asks the same question, but it has a completely different method, right? Okay, I will just go on. So very quickly, we can identify two main approaches within paraconsistent set theory. So paraconsistent set theory is simply that you take the axioms, the theory axioms of some set theory, right, which could be naive set theory or Semmelweis-Frenkel set theory, and then you combine them with the logical axioms of a paraconsistent logic. This is how you normally would define a paraconsistent set theory. And within this, you have these two main approaches: the naive paraconsistent set theory approach and the iterative paraconsistent set theory approach. And as the name suggests, the true non-logical axioms of paraconsistent set theory are extensionality and unrestricted comprehension in the case of naive paraconsistent set theory. Just to make a point on this. So normally you have like this division into, if you follow a dialectic program, you would normally say, okay, you have the material approach, the relevant approach, and the model theoretic approach, which were first presented in Priest's In Contradiction. And I think all these approaches have the problem, which I was pointing out in the previous slide, that you don't get really interesting models, right? In the case of the material approach, you have model theoretic problems. You cannot define certain sets, or you get a gluty single element model. So it's not very satisfying. In the case of the relevant approach, you have these problems with sets which are identical, but extensionality is too weak to say that they are not, that they are identical, which is called the doppelganger problem. And in the case of the model theoretic approach, it's very interesting. It's actually, you could say it's the first model of paraconsistent set theory, because you get a model which validates Semmelweis-Frenkel, and at the same set theory which is called NLP, which is simply naive set theory with the logical axioms of Priest's logic of paradox. However, you also have some problems there, because then you need kind of to assume that Semmelweis-Frenkel is consistent, and this is an assumption which a dialectist, I don't think he has a lot of resources to make this assumption. Again, this is something we can discuss afterwards. But I'm not following here the criticism by Meadows, but rather by Incorvati. I think Meadows was wrong. I think he misread Priest. But I think Incorvati has Luca Incorvati in 2020, he has this book, Foundation of Mathematics and Conceptions of Set. And he very convincingly argues that this is an assumption that a dialectist cannot really make. Okay, but we can come back to this. And just to make, this other point, we don't follow this naive paraconsistent set theory approach. But we believe that the right way of doing paraconsistent set theory is to combine the Semmelweis-Frenkel axioms with a paraconsistent logic. Okay? So this is like the first philosophical contribution of our work, of our recent work. I think we're the first of really putting this in words and saying that instead of following this naive approach, we should maybe rather focus on iterative paraconsistent set theories. Why? Because the models that you become they resemble very, very closely the cumulative hierarchy. So you get actually natural models. And we will also argue that these models are mathematically expressive, and they have what we call they are faithful to their conception. I will come back to this later and be more precise about this. But let's just say that you get expressive models, so you can really do mathematics in these models, and at the same time, philosophically speaking, I think they're well motivated. Okay. So we have the naive approach, the iterative approach. We follow the iterative approach. Okay. And now I will talk about how we build these models. What is the methodology? What's the strategy of building these models? And very briefly, I will talk about Boolean valued models, then how to generalize Boolean valued models. Then I will talk about the work of Loewe and Talafter, which was the stepping stone, so to say. And then I will talk about how we extended these models. Okay? So the intuition of any Boolean valued models is to simply replace each set in the cumulative hierarchy with a two-valued function, with its characteristic two-valued function. Okay? So you take any set X, and then you ask, is the set inside of X? And if it's inside, then you assign value 1 to it. And if it's not inside, then you assign value 0 of it. In this way, you can characterize each set in your cumulative hierarchy with its characteristic function. Okay? But there's a problem because the element of a function does not necessarily have to be a function. It could be simply not a function. And this is what's called homogeneous functions. So you want the elements of your functions to be two-valued functions and the elements of these functions to be two-valued functions, etc. So you need a definition by recursion. So you can define the universe of two-valued homogeneous functions, which short is just the universe of two-valued functions. And then you build a hierarchy by transfer net recursion. So you say that at the stage alpha, you simply have the two-valued functions where the domain of these functions are two-valued functions which have been built in a lower level. Okay? You see? This is why the range is 2. And the domain of this function x will be a subset of a lower stage. Okay? So you start with empty set, then you map empty set to 1, empty set to 0, and then these sets you map it to 1 to 0, etc., and then you build up your hierarchy. And if you collect all these two-valued functions, then you get the hierarchy or the universe of two-valued functions. And this model, this two-valued function universe, this universe of two-valued functions, is isomorphic to your cumulative hierarchy. So this is really the cumulative hierarchy, in other words. Oh, okay, it's not really the cumulative hierarchy, but because you have a duplication of elements, but you can show that every sentence which holds in the cumulative hierarchy will also hold here, and vice versa. And now the first generalization of this method is to replace the Boolean algebra 0 and 1 by any complete Boolean algebra. So now we can define the universe of b-valued functions. So the only thing which changes now is that the range of your functions will be much bigger and can be any Boolean valued model, be a Boolean valued algebra. Okay? And as soon as you build these Boolean valued models, you need a language, because until now you just have a universe, okay? So now you build a language, which is the extended language of set theory, which is simply the language of set theory, where we have just a first order language with a binary predicate, which stands for membership. And then you add constants for each of these functions. The names of these functions are called simply names. Sometimes they're referred to as B names, or depending on the algebra, A name. But yeah. And the formulas in the sentence that you build in this extended language of set theory are called B formulas or B sentences, or simply LB formulas or LB sentences. Okay? And then you go on and you define an interpretation map. This interpretation map goes from the extended language of set theory and maps each formula into values of the universe of the Boolean algebra. Okay? And these values of the Boolean of the universe of the Boolean algebra will act as truth values. Kind of. Yeah. So in the case of Boolean valued model, we can say that the sentence phi in the extended language of set theory under this interpretation map receives value 1. This means that this sentence is valid in my structure VB. Okay? And then we can denote this fact in this following way. Now we will go on and say how this map is specifically defined. And I will talk first about the atomic formulas and then about any formula in the language of any, how do you call them, complex formula. So first of all, notice that this definition, the following definition, is given by recursion on the hierarchy of names. They are, how do you say it? They are by double recursion. So here you have identity, and here you have membership, right? They are simultaneously defined. And we say that a function u is inside of a function v in the case that there exists something in the domain of v, so let's say an x, such that this x is equal to u. And this join in front is simply like a quantifier, like an existential quantifier. So we want the best possible or the closest one which is identical to u, right? So if I want to calculate the value of u in v, then I will go through every element in v, see if there's some element which is identical to u. And of this, all these values, I take the highest possible value. This is it, right? And for identity, it is simply extensionality written out. Remember that this the big join here, it's simply like a universal quantifier. So I'm saying u and v are identical in the case that every function in u is also in v. And similarly, for any function in v, it has also to be in u. And here I collect all this value, and then I take the lowest possible value. Okay? Yeah, but if you have not seen this, think about it as extensionality. Okay, here we have the interpretation map for complex formulas. So this is now given by recursion on, not recursion, by induction on the complexity of formulas, okay? And the only thing you should notice is that on the left-hand side, these are operations in the algebra, okay? This is a binary operation in the algebra. And this here is a symbol of my language, right? This is a conditional, but this here is a binary operation. Similarly here you have the other way around here, right? So here you have the negation in the language of set theory, and here you have the unary operator, which interprets negation in the language of set theory. Okay, so here, language of set theory, and on the right side we have the operations of my algebra, of my lattice. And this is also what I meant, that the join and the meet respectively interpret the quantifiers, right? And this is also why you want that your algebras and complete bonded distributive lattice are complete, because you need quantifiers. Otherwise, you cannot interpret your quantifiers. Yeah, okay, I will just go on. And then you have this lemma, which is very interesting, because if you read it straight away, you would say this trivially holds for any construction. And in the case of Boolean valued, Heiting valued models, this holds. This is what we will name bounded quantification property. So for any B formula, we saw what it's a B formula with one free variable x, and add all u names in VB, the following holds, okay? So notice that this is not trivial, because here, this is an abbreviation. It should say exists in x, parentheses, x is in u, and formula, right? This is a bounded quantifier here. And what happens actually is that you have a hidden quantifier here. And in the case of the existential quantifier, it's quite trivial, because you get two, how do you call it? You can get two big joins, and then for any very basic algebra, this will hold. But in the case of the universal quantifier, this is quite problematic, and this will break down, because here you're just looking in the functions of u, but here this for all x will refer to every possible function that you have in your universe, okay? So this might not coincide. Okay, and then the very basic result that you get is that for any complete Boolean algebra and for any filter, we have that VB satisfies the Semmelweis-Frankel axiom plus choice. Just one thing, I have not written some subscript here. Sometimes I will write a subscript in the case that it's not for any filter. If it's for any filter valid, then I just will write it like this. Okay? And further on, this will become more clear. But this is a very impressive result. And then let us think about generalizations of Boolean valid models. And the first case are Heyting algebras. So similarly to the case of Boolean valid models, in any complete Heyting algebra or in any model constructed above a complete Heyting algebra, we also get the validity of ZF, of Semmelweis-Frankel set theory. Okay? So actually you get IZF, but ZF and IZF in this context of algebra valid models are normally equivalent, because the only thing which changes is that instead of replacement you have collection. But in any case, this is just in detail. And now, how can you think about other non-Heyting algebras, right? Do there exist other algebras which allow us to make this construction, which allow us to build models based on algebras, which still satisfy the Semmelweis-Frankel axioms? And then you have this very impressive result by Shurav, right? Which says the following. Take any complete bounded lattice of this form, right? So if a universe, you have the mean to join the binary operation, which is like a conditional for us, 0 and 1. And if this lattice satisfies 4 properties, which are called P1, P2, P3, P4, then we call it a Dree algebra, right? If it's a Dree algebra and we get the bounded quantification property for negation-free formulas, this NFF means negation-free formulas, then in this model, extensionality, pairing, infinity union, negation-free replacement, power set, and negation-free separation will hold for any filter, right? They will receive value 1. And this is very impressive. And this was kind of like the stepping stone. This was because if you now want to build a non-classical model, which is not Heyting and not Boolean, then you will simply try to find an algebra which satisfies these properties, P1, P2, P3, P4. And then you check if in the model the negation-free bound quantification property holds. And then you already know that you get a model of negation-free Semmelweis-Frankel. Okay? So this is a very, very impressive theorem, and we basically use this throughout the whole thesis. Just one point. We also showed that this theorem is not, that you can go around it. For instance, if you take Bree's logic of paradox, then it's not a Dree algebra, right? And you still can build a model of Semmelweis-Frankel. So there are certain ways around this. But then, for instance, we had to modify the interpretation map and do other stuff. Yeah. Okay, so let us talk about the stepping stone, about the first, well, yeah, I will call it now the first model of a real para-consistent set theory, which was again provided by Shurav and Benedict Löwe. And they have the following example. You take the tree-valued algebra PS3, and here the star will interpret the negation, and you show it's a Dree algebra, and you can show that in this model, the negation-free, the bound quantification property holds for negation-free formulas. So actually what they do is they start out without the negation. And then they show that it's a Dree algebra and that the negation-free, and that the bound quantification property holds for negation-free formulas. And then you get this corollary. You get the negation-free fragment of ZF in this model. And then you can show that this model is non-classical. In particular, you show that it's para-consistent. So you find a language, you find a formula, a sentence in the language of set theory, such that the sentence holds and also its negation, right? And you know it's non-trivial because, I mean, you know that, for instance, extensionality get value 1. So the negation of extensionality will get value 0. I think one thing I have done wrong in my thesis is that I was not very precise about my definition of para-consistency. And normally if I showed, when I showed that a model is paraconsistent, I used this. So I showed that there's a sentence such that phi and not phi holds. Because I already know by the construction that there are sentences which will get value 0. So the law of ECQ, the quad limit, it will not hold, right?
Santiago,
Yes, please.
is the implication table where 0 0 should be 1, right? It is written 0 here, I think.
Oh, yes. Sorry. Yes, completely true. Yes. So in the right corner of the implication, it says 0 0 0, and this last 0 should be 1. Yeah. So actually, thank you very much, Olaf. So what goes on is that if you have a positive value, some value which is not 0, and then it goes to 0, then it just gets 0. And for the rest of possible combinations, you get always value 1. Yeah. Thank you, Olaf. And this is truly the first model of paraconsistent set theory, or it's in conflict with Priest's model, but yeah. And okay, now you have one model. You have found one model through algebra-weighted models, which is paraconsistent. And here's where me and Giorgio started, and also Rodolfo. And the first step was to extend this result to a whole class of models. So at first you had this one example. Now we want to show that we have a whole class. So in the case of Boolean value models, you have also a class of Boolean algebras which give you models. Here you had just one model. So the first step, or the first contribution, was to show that this result also holds for the wider class of algebras. And what we first did is that we had to look at joint complemented lattices, and it didn't work. So we had to look then at meet complemented lattices, and then it worked somehow. And this is a simplified definition. So you can take an algebra of the following form. So this here is a complete bounded distributive lattice, right? The base set, so A, which is the universe of the base set, is totally ordered by the less or equal relation. And the implication is defined in the following way. So if A, for instance, is not 0 and B is 0, then A implies B will get value 0. And in any other case, A implies B will get value 1 for any two elements. What happens? If I think about, we call this totally ordered implication algebras. First of all, we showed that they are all tree algebras, right? We also checked that the bounded quantification property holds for negation-free formulas. And what now happens is, if you look at the two-valued case, then you get V2, the two-valued universe. So you get a classical model. If you look at the three-valued case, you get the model that we just saw, PS3 star. And then you go just up, right? So you have, these are all chains. Then you have the four-value chain, the fifth value chain, etc., etc. And then we have the following results, right? Let T be where T are these algebras, right? Let T be any totally ordered implication algebra. Then we can show that we get the negation-free fragment of Semmelrau-Frenkel minus foundation. Okay? Because if we go back, here, foundation is not included. Foundation we always have to show separately, but normally it will hold. I say normally because normally you assume that your base set is well ordered, but in the case it's not well ordered, you could also produce a model where the negation of foundation holds. And this is actually what we did afterwards. So you get the negation-free fragment of ZF minus. And then if we restrict these lattices to just well-ordered lattices, right? So instead of saying that this is totally ordered, we say it's well-ordered. Then we actually get the negation-free fragment of Semmelrau-Frenkel, right? With foundation. So this is kind of a very nice result if you think about it, because now you have a class of models which are paraconsistent. Well, here I would say that they're paraconsistent, and you get a negation-free fragment of Semmelrau-Frenkel, right? And as I was hinting, if you choose a suitable filter and a negation, then you can show that any complemented well-ordered implication algebra is also paraconsistent. So you have a sentence phi in the language of set theory, which holds, and also its negation, right? How does this unary function works? Basically, 1 is mapped to 0, 0 is mapped to 1, and any other element of the chain is just mapped to itself. We used to call this the reflexive operator also. In the very nice result, which I think it was published right now, I think 1 week ago or 2 weeks ago by Shurov in the Journal of Symbolic Logic. It's called, it's an article called Non-Classical Foundations in a Class of Set Theories. Okay, in any case. In this paper...
Yes. Foundations of set theory.
Yes, thank you, Shurov, exactly. So it came out right now. And what Shurov showed is that you can take any model that we just talked about. And actually, in these models, they are so similar to Boolean value models that you can take any argument which involves cardinal arithmetic. And if this argument holds in the Boolean value model, in the classical model, then it will also hold in this paraconsistent model, right? And this is a very impressive model because, for instance, if you base it or if your ground model, for instance, verifies choice, then you also get choice. You can show that you have mathematical induction, natural numbers, anything, any principle in cardinal arithmetic seems to hold. So this is very, very, a very nice result. And this was the first criteria that we imposed, right? That we want mathematically expressive models. So it really works in a certain way. And then a kind of a curiosity. If you choose another negation, this is the meet complement actually here. So if you think about the chain, 0 gets mapped to 1, and every other element which is non-zero now will get mapped to 0, right? So 1 goes to 0, and everything in the middle of the chain will go into 0. If you define a negation like this, then you can show that these complemented well-ordered implication algebras give you a model of full ZF, which is also kind of impressive because before this, you didn't know if this was possible. Before this, you always assumed that you only get a model of full ZF if you use either a Boolean algebra or a Heyting algebra. Now we showed no, it's not true. We have a bigger class of algebras which allow you to produce non-classical models of Samuel-Frank, right? However, there's a little drawback with this because modus ponens does not hold. So I guess Graham, for instance, will say that this is not a real model because if modus ponens doesn't hold, you don't get a model of the whole theory, right? There will be consequences of the axioms which will not hold or which you cannot derive. So yeah, this is a drawback. But also just to make this point, more recently, me, Shurov, and Georgia, we showed that you can find models of full ZF and you got modus ponens. Yeah, just this clarification. And something very interesting about this model is that it's not classical, right? It's non-classical, but at the same time, it's also not intuitionistic, right? It's not paracomplete. So it's neither paraconsistent, neither paracomplete, nor classical, which is kind of curious. And then just to show that we have an application that we can use these models to do something is we gave a very simple proof showing that we can construct models where the whole set F minus foundation holds and the negation of the foundation axiom holds. So we managed to do a forcing proof in a very simple setting, right? So if you think about this, Boolean value models were always thought about as a simplification of the forcing method, of the partially ordered set forcing method in set theory, right? And we showed that in a non-classical context, we have this application, for instance, which should also be interesting for a classical set theorist. Okay, so this was also a kind of nice result here, theorem 5.9. And the trick, as I was saying, is that you simply replace this totally ordered algebra with an algebra which is not totally ordered. You simply take a non-well-founded algebra. Actually, we take an algebra which is isomorphic to the structure of the rational numbers, and then it works. Okay. And this is like the first big chapter And now I go on to the next section. Playing around with negation. So one problem we had is that we had all these models now, but we didn't know if they're different. So we were unable to show that there exist sentences which differentiate these models, which is kind of messed up because you want different models. And with the particular negation we chose, it was impossible. Maybe there's a way, I don't know, but we didn't manage to do it at that point. So our idea was to simply expand well-ordered lattices with different unary operators. Because you see the theorem I showed you of Schurter, it holds always for the negation-free fragment. So you don't have the negation there. So you can simply put in any negation that you want to put in there. And then we said, can we really use any negation? And we started to thinking about like, what is a negation? What in this context, in the logical context, is a negation? And I will come to this in the next slide. So we found this negation, which is called predecessor, also successor, because what happens is the following: 1 goes to 0, 0 goes to 1. And then, for instance, in the predecessor, it will always go to the lower element. It goes down, tick, 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 tick. And in case of the successor, it goes up, tuck, 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 right? So for instance, if you think about a 4-valued lattice, where you have 1 on the top, then it goes to 0, 0 goes to 1, and then, for instance, you take the, how it's called, the atom, and the atom will go 1 step up, right? And then the coatom will go 1 step up. Yeah. And this is why we call them predecessors and successors, because, yeah, they always do 1 step or higher or 1 step lower. And then we could show, so just to make a point of this predecessor and successor, intuitively speaking, they are not negation-like. They don't satisfy any regularity property that you would like a negation to have, just as contraposition or double negation introduction, double negation elimination, etc. So predecessor and successor, they don't satisfy anything. But if you add this predecessor or successor to our totally ordered lattices, then you can actually show that you get paraconsistent models, and each model is different, which I call non-epsilon elementary equivalent. See? Yeah. So we say that two models, they are non-epsilon elementary equivalent in the case that you can find one sentence in the language of set theory which holds in one model for the filter, but does not hold in the other model for a certain filter. Okay? And this is an interesting result because at the end, this is the first, though very basic example of an dependence result in a paraconsistent set theory, right? And just to make also a point on this, Schurter and Giorgio, I think it came out this year or last year in the review of symbolic logic, they found a whole new method of doing forcing for paraconsistent set theories. And there can be done much more than here. But this was chronologically the first attempt of having a very basic independence result. Okay? In a non-classical set theory, of course. Okay, and then, as I was saying, we asked ourselves, what is a negation? So we went a little bit to the more philosophical debate. And you have the American plan, which says basically, okay, it's a switch operator between truth and falsity. And you have the Australian plan, which says, no, it's a ruling out operator. And normally the Australian plan is coupled with inferentialist conception of operations, of logical connectives. So in the case of the Australian plan, we say that that a certain unary operator or a certain logical connective satisfies the Australian plan for being a negation in the case that it satisfies double negation introduction and contraposition, right? And we went through every possible unary operator on these lattices, and we didn't manage to find one which satisfies these both properties and at the same time gives us more expressivity in language so we can distinguish these models. It was all the opposite. What we observed is in a certain way a trade-off between the regularity properties of negation and the expressivity of our language in our model, right? So what we said at the end is, okay, nobody can tell us that, for instance, the successor or the predecessor is not a negation. Because at the end, in an algebraic context, it's just a unary function which goes from one place to another place. So this is what we call basically the minimal account of negation, which says that the negation telepaths point in a relational structure. This is basically the definition. That is a device which linguistically allows us to distinguish semantic situations from each other without committing to their validity. And then you can notice that this is more basic than the American plan and the Australian plan. It allows for much more negations. And then you could also say, but maybe it allows for too much. And we say still we can identify different kinds of negations. For instance, the classical-like negation and the intergenistic-like negation. I will just give an example of the classical-like negation. We call a negation, or we call a unary operator a classical-like negation if the negation does loops. So if it at a certain point comes back to its initial point, right? And yeah, we showed that we have certain intuitions that we can identify with classical-like negation and intergenistic-like negation. But again, this is a topic that can be worked out further and has to be studied more. And okay, this is the second topic. So now we showed that we can find infinitely many models for paraconsistent set theory. We showed that we can find different models if we play around with the negation. And then I will show that if you not only play around with negation, but with the lattice itself. So if you choose lattices, very expressive lattices with a good binary operation, which will be our conditional in the language of set theory, then we can also find other models of paraconsistent and paracomplete set theories. Yeah, so basically here we define this lattices, this structure, this class of structures. We call them Heyting implication lattices because basically we take a Heyting lattice. So this is a complete bounded distributive lattice, which is totally ordered and finite, okay? And with a binary operator, where the implication is, so this is basically the definition of the binary implication in a linear Heyting algebra, right? So if A is bigger than B, then it gets value B, right? And if A is less or equal than B, then it will get value 1. Sorry, here, there should be a 1 here above the B. And just one point, why do I focus throughout the whole thesis on always totally ordered lattices? It's for the following reason. Schuraf and Benedict and Passmann in another paper, they showed that if you have a non-trivial automorphism that you can define on the algebra, then the elements that you can exchange by this non-trivial automorphism, they will not be in the range of your model, of your interpretation function in this model. So they will simply not occur. So for instance, if you think about the diamond, the four-valued diamond in the case of the four-valued Boolean algebra, then if you look at the range of this model, then you will simply have 1 and 0. So A and B, which would be like the corners of the diamond, they will not get any value. This is what I had in mind always, why I used rather totally ordered and also finite lattices. But again, you can extend this to wide class of algebras. What you really see, what you really need is an atom and a coatom. Otherwise, the existential and the universal quantifier will do very strange stuff. Yeah. But yeah, there are ways around this. You can extend this to bigger class of algebras, etc. So we know as corollary from the theorem I showed you from Schuraf and Benedict that if A, or if I have a Heyting application lattice, then the respective algebra valued model will validate also a negation-free fragment of Samuel-Frank. So now I simply have to show it's paraconsistent. And this is very easy. We can take, for instance, the reflexive operator. So 1 goes to 0, 0 goes to 1. Every other element of the chain will go to itself. And then you can show that you have, again, a sentence in the language of set theory, phi, and phi will be validated by if you choose a certain filter, and also its negation, right? And now, if you choose different filters, you will get different logics for these models, right? So if you have any filter which extends the top element, then it will be paraconsistent, right? But if you now choose a filter which is not the ultra filter, so it doesn't include the coatom, right? Then you can show that these models are paracomplete because the law of excluded middle will fail. So what happens is that you can define a sentence in the language of set theory, which always in any of these models will get mapped to the coatom. and since the coatom is not in the filter, because we've chosen a filter which is not a virtual filter, this law will not hold. And given the validity of double negation elimination, we also know that the logic of these models is not intuitionistic propositional logic, which is also kind of interesting. I know that the professor of Schulhoff is, how do you say it, his supervisor, he's interested in the logic of these models. I think he was looking at this. What happens if you take a Heyting algebra and then you have a paraconsistent negation? But I have not worked on this part. This is also work for the future. Again, if you now choose any filter which extends the top filter, but it's smaller than the ultra filter, then you will have models which are pattern complete and pattern consistent, right? This is how this lemma reads. And this is a theorem. So if there are mistakes in the thesis, I think it will be in this theorem and the theorem I need for this theorem. We can easily show that these models are also different. So they are non-epsilon elementarily equivalent, right? From the other models that we constructed and in between themselves, right? So we get really more different models. Yeah. So we get this theorem, take any two Heyting implication lattice of different cardinality. This is why they have the sub-indices n and m. And then you can show that if you choose a suitable filter F1 and F2, that these models are different, validate different sentences. And something interesting, what happens here is that in the case of the totally ordered lattice models, only the membership relation is paraconsistent or is non-classical. The identity is very classical-like because it will always get 1 or 0. So if you remember, the definition of identity includes only the meet and implication. So if the implication only gets 1 and 0, then you know that the identity in your model will also just get 1 or 0. But here, since, for instance, 1 implies A will be A, you also get a non-classical identity, which makes them different from the models that I just presented before. Yeah. So this is the first way of twisting these models, really, is to look at different lattices and very expressive lattices and then expand them with different operations. For instance, you can do the same in Boolean algebras and then put a paraconsistent negation in. You can do a lot of stuff. And I just looked at the linear and finite case in this case, but you can extend it for a much bigger class, right? And then another very interesting application or an extension of this work was that we said, okay, what about not only modifying the structure of the lattice, but also modifying the definition of identity and set membership in our models? And this is how this work was motivated. Because if you go to Schulhoff's theorem, you need these properties of being a dry algebra. But LP does not satisfy these properties. Actually, LP is a quite strange logic because, as you will observe, modus ponens will not hold for this model, for this logic. Neither disjunctive syllogism, etc. So it's in a certain way very weak. It's a very intuitive logic, I think. It's very intuitive in a certain sense, but at the same time, it's also very weak because of the lack of modus ponens. And we showed that if you do this modification of the interpretation of set membership and identity, then you can actually build a model which will satisfy ZFC. Again, you don't get modus ponens in this model, right? So it's a model of the axioms of set theory, not of whole ZFC in this sense. Yeah. Again, the first idea when we built this model was to straightforward, this is like the first attempt, which didn't go very well, it's just to take the latest and then do the regular construction we did before. And what we saw is that precisely because of the lack of modus ponens and other basic inferential features, there are many properties which not hold. And I cannot say that you don't get the model, but I can say that it gets very difficult to do the calculations because all the properties you normally need, you don't get them. So you would have to really rethink how to get these properties. And one of these properties, for instance, is the Leibniz law of indissolubility of identical, which means if two elements x and y are identical, then they should satisfy the same properties in your language. Okay, and this will fail, obviously. And something also interesting is that you have a collapse of zero-like elements and one-half-like elements. So I say that an element, a name in my model is zero-like in the case that it's either empty or the range of all the elements in my function gets value 0, right? And similarly, a one-half-like element will be an element where the range is always 1/2. And all these models collapse to the empty set, basically. And you also get non-well-founded sets, which is very interesting. But again, you are kind of stuck because you cannot do a lot. You don't get bond quantification. You get kind of stuck in this construction. And then we say, okay, let us play around with the membership and identity. And just one point. So in the same time, or actually it was before, should have Giorgio and me, we thought about the totally ordered lattices and doing the same, modifying identity and set membership. And this allowed us to find models of full ZF which are paraconsistent. And we claim that these are the first models, the first true paraconsistent models of ZF. I think this is up to discussion. I think Graham will have some thoughts on this. Yeah. In any case. So you have, so the set membership stays basically the same, but now look at the identity. So remember how it was defined before? I will just very, very quickly go back. This is the standard definition of identity, right? Extensionality. Now we will go back, just 1 second. And now we're doing this. So I'm saying, if I have one element or one function in the domain of U, and the value of this characteristic function, so the value of x in U, is bigger than the value of x in V, then it automatically gets value 0, right? And you see that, for instance, if you go back, the problem is this. For instance, 1/2 implies 0, 1/2. You don't want this in your identity. But now, if you have something which gets 1/2, say, in one element and 0 in the other one, then it automatically it's blocked, right? So there will really look as different functions. And the idea is basically that you want a classical notion of identity. You want to bring the notion of identity that you have in your models and the notion of identity in your meta theory. You want to bring them closer, so you get certain properties like the Leibniz law. And to make it very quick, it works. You get a model, you can construct a model of LP using this interpretation map, which I put here the subscript IN to differentiate it from the other interpretation map. Then you can really show that a model based on this, and if you take the positive filter, so the filter 1 and 1/2, then the Semmelov-Frenkel axis plus choice are true in this model, which is also a kind of nice result because in the model of Graham, you have two basic model constructions. The first one, which is the type lift, which I think is problematic because you kind of cut the hierarchy in 2 parts, and then you get something above a certain inaccessible cardinals, call it kappa 1 or kappa 2, and everything above is collapsed to a single set, and everything below stays as it was before. I think this is a very strange representation of the universe of sets. Again, Graham himself, he criticized this construction. He also says that he wants something more refined models. He wants that different instances of comprehension are validated by different sets, right? And then there's another way of building this model, which is the Heimkens type lift. But then again, in the Heimkens type lift, you lose the law of Leibniz, so which is also not very nice. And here it holds really. So, but again, in Graham's models, you get modus ponens, so you get really a full model of Semmelov-Frenkel plus choice. You can really derive everything from it classically. In this model, you can't, right? So there are differences. There exists a certain trade-off. And again, it's not a problem that it does not, that in Graham's case, it does not satisfy the Leibniz law, because if you simply want to show that it's possible, then he has shown that it's possible. But still, you can, yeah. it's a trade-off. I guess there will be some discussion on this. And just to make this a little bit more precise, to point out the differences of my model and Graham's model. In my model, you don't have the validity of comprehension. So comprehension will not hold. So we have really different theories, right? And as I was saying, since you don't have modus ponens, not all the theorems will be derivable from ZF, right? Sorry, here the interpretation map is missing. And as I was pointing out, you have a certain trade-off. In Bree's case, you get ZF and all of its theorems. However, you're forced to non-classical notion of identity. And I think this is kind of a drawback, this non-classical notion of identity. Also, the axioms in the case of Graham's model, they hold inconsistently. So if you have contradictions and you look at separation, then you will have that separation holds, but also the negation of separation. In my model also, but for instance, in the model that we built with Shurov and Giorgio, you get really a consistent model of full Semmelov-Frankel, right? So it is different. And in our model, we validate the theory axioms of ZF Semmelov-Frankel plus choice with a classical notion of identity, but we lose some theorems of Semmelov-Frankel. And kind of the lesson that you can learn from this is that forcing identity to behave properly within our algebra-weighted model is unfortunately not enough to obtain a full model of all the theorems of Semmelov-Frankel plus choice. Yeah. And now I will very, very quickly talk about the conclusions. I don't know how my time is, but I guess I'm okay. What have we shown in these 4 years? We can build infinitely many models of paraconsistent set theory, which has not been done before. In particular, the resulting models are mathematically expressive and faithful. I claim that they're mathematically expressive due to Shurov's results. And this faithful notion, I don't know if there will be a question on this, but faithful basically means that it's coherent with its underlying conception. And in the case of our models, the underlying conception is iterative. But since we precisely get models which imitate the cumulative hierarchy, these models are really also faithful. So you don't have a conflict as in the case of naive set theory, I think. We showed that we can find non-classical models of full Semmelov-Frankel, which are neither classical paraconsistent nor intuitionistic. This was also a novelty. And we have provided new techniques for constructing algebra-weighted models, such as modifying the operations of the underlying algebra or modifying the interpretation. So now any student can come and he wants to build a non-classical model of set theory, and you could take my thesis and say, okay, maybe you can follow the strategy and start playing around with either the interpretation map or the operations in my algebra, and it might work. Yeah. And then the fourth conclusion, this is a bit trivial, right? We have shown that the pluriverse of sets is a little bit wider than expected, because this iterative conception of set can be realized by much more non-classical logics than we normally would assume. Yeah. So after this, you can really say that iterative conception is not really classical. You can really argue that it should be not bounded to any logic. Yeah. But again, this fourth point needs more argumentation. It needs a little bit more work. And yeah, also my thesis, I was too quick on this. And also just to make some self-criticism, I think this is a kind of weak part of my thesis, the introduction and the conclusion. I think this needs a little bit of more work, a little bit more philosophical work and argumentation. And also there's one theorem, say, in the chapter concerning the paraconsistent and paracomplete models, which I'm not 100% sure about. I know that the intuition works, but the way of saying it, I think, could be improved. Yeah. And just for future work on the logical side, one thing which has not been done is to develop the first order version of LPS3, which is LPS3 is simply the logic that we get if we look at. So it should be LPS3 with the star. I forgot about the star here. Yeah, to think about the first order logic of this PS3 weighted models. Yeah. And we also maybe can look more at the logics that we have produced. So we could axiomatize the logics that correspond to the constructor models of set theory. Yeah, this is a part that I have almost completely ignored, but there's a lot of work here, and as we've shown, there are different models and they will have different logics, and it would be interesting to look at this logic. Maybe these logics are already explored and they are well known. In this case, it would also be interesting. But yeah, and on the algebraic side, something which is still open is that we want to determine the class of algebras such that the logic of the respective model of this algebra is PS3, right? So we have found this huge class of totally ordered valued models, which all have the same logic, PS3, but maybe there are more models. And the logic of these models is also PS3, right? So really to find out which is this class. And if I'm not incorrect, should have said that some people in India might be working on this. Yeah. And then the other big, very, very big task is to find the class of algebras that are able to give rise to models of ZF. I think this was also a motivation at the beginning of the work to really find the biggest possible class of algebras, such that when you construct a model on top of it using algebra-based models, then you get the model of ZF or the negation-free fragment of ZF. Yeah. This is something which is an interesting open problem. And then on the more set theoretic side, and this is the most interesting future work or future direction, which I think should be explored, is now generalizing this modification of interpretation maps. So I made the hypothesis that you can probably construct for any non-classical logics which satisfy some minimal requirements now models of ZF or similar Frankel-plus choice. Now I'm not so sure anymore because the in-interpretation function, so the interpretation function for Boolean for LP, it first of all, it doesn't work for all the Boolean valued models, and it does not work for Heiting valued models. So again, it would be a very nice task if you can find an interpretation map which works for everything, for Boolean valued models, Heiting valued models, and non-classical models. On the other side, I'm not sure about this. I'm showing this right now. I think it holds for most of De Morgan models, De Morgan algebras. And in the class of De Morgan algebras, you have a lot of interesting non-classical logics, such as Breeze LP, Bell-Napdam logic, etc., etc., etc. So right now, I was showing that it might work for Bell-Napdam. But yeah. And another direction which I was exploring with Shurav and Georgi was to build then quotient models. I personally think that these quotient models might be more interesting if we focus on Heiting lattices, because these Heiting lattices are more expressive. You really can say more, identity behaves more non-classical. Maybe it's also more problematic because of this, but this is something that has or should be explored. And then if you really want to do forcing at the end, you need a more complex stone space. So the stone space in the case of Boolean valued models or Boolean algebra is the collection of ultrafilters, right? And since we just have one ultrafilter, we will get simply a single point in our stone space, which is not very interesting from a forcing perspective. So yeah, so finding quotient models with interesting stone spaces, this would be like the perfect situation to explore pattern consistent forcing. And another direction would be to explore really analysis and maybe topology, because if you have analysis, then you can look at more complex set theory. You can look at maybe some combination with transformed game theory. I don't know. This has to be explored. But at least analysis and thus also topology, I mean, they're very connected, should be able to be reproduced in these non-classical models. Yeah. And on the more philosophical side, I think a nice future project would be to extend the ideas of the Gödel program to these non-classical set theories. So really see if you can carry over what you do in the classical case to maximize interpretative power in the case of non-classical set theories. So what you really want to study at the end is independence and justification in a non-classical set theory. And that's it. That's everything I have for now. These are the references. Here's Bell's basic text, our publications also. And this was Schuler's article I was mentioning. Yeah. Okay, that's it. I don't have more. I think I have talked way too long, so I'm very sorry. And I will stop sharing right now.
Thank you very much, Santiago. Just a question for everybody. At some point, we probably will take a small break. Do we want to take it now, just before to recollect ideas, or we go on as you want?
So coffee break now?
Giorgio, can I ask a question? How long do you envisage this going on in toto?
I don't know. It depends on you guys, but I guess still 1 hour or 1 hour or two, depending on the questioning. So, any preference?
No.
Well, if not, I mean, we can go on, and then when we are tired, we can just take a small break. So, I mean, again, thanks, Santiago, and for the presentation, everybody for being here. As usual, then we start the questioning from the member of the committee. And as usual, we start with the one who's coming from Father. In this case, it is Shraf. So please, Shraf.
Well, thank you very much for inviting me here in this committee. And of course, like before asking the questions, just let me tell you that in a 1 year I worked in Brazil with you guys, like Giorgio and Santiago. Like it was very nice, and like in that year, like Santiago's PhD thesis was going on. He was working on his thesis, and the experience for me was really nice. We enjoyed and we worked hard, as I can remember, and as a result, like we can see very nice results actually came up in different papers. We three together, and then Giorgio and Santiago, and also the theorems and the propositions Santiago got in his thesis is really commendable. So this is the first point. Of course, like I'm of course a bit emotionally attached with this thesis as well, the thesis of Santiago, of course, because it is a generalization of whatever I did in my thesis. So he actually has extended the things, he extended the results, and he got more models on this. And but of course, like there are few questions which I actually wanted to ask, and this is the right platform to ask the things, and which are like this. So first of all, Santiago, which I wanted to ask you, you mentioned at the very beginning of your presentation that, of course, that you have classified the paraconsistent set theory in two ways, right? So one is the naive way, another one is the iterative way, right? And you said that you actually went for the iterative one, right? And I can remember that once I talked to Jack Weber in India, long back, like when I was doing my PhD in 2011-12, like that. And then whatever he said that why to take this way, like his motivation was to take the naive way, actually. Okay, and we all know that the work he actually is doing. So this is the first question to you, that why you consider the iterative one is the best one and not the naive one?
Thank you very much for this question. So I would say basically because you get no natural models in the case of the naive case. And yeah, this is basically, I think, the main argument.
Oh. Does that mean that if in future someone come up with like a proper concrete model of naive
Yeah.
thing, then will the
then it's
change?
then it changes, of course, yes. Yes. So I was very curious about the book of Sakueva. I started reading it, and yeah, but I think Sakueva and we have the same intention. We want to know how much mathematics or classic mathematics we can do in a paraconsistent set theory. So it's very interesting to compare the results, and yeah. But I like a lot. I like a lot the naive proposal. It's very, very good. It's philosophically actually very sound and well motivated, and it's beautiful. This is also why my thesis I started talking about the paradoxes and then how it's different from the iterative conception. Yeah.
Okay. Of course, it is connected with this question that you see, we have already seen that the previous works on paraconsistent set theory, like they are always like people took the comprehension axiom, the generalized comprehension one, and as a result that we have seen that the Russell set, that collection of the Russell sets and the collection of all sets, like these things are sets, right? They have worked it like this.
Yeah.
But in the constructions, what you did, like the Russell set is not anymore a set, is not a set, is not in the model. So how do you see these things? Like which one to take? Like it is connected with the previous question, but anyway. So
Yeah.
because
Well,
what Jockwich said, I can remember that he told that what's the problem, like to take the Russell set as a set. Like you understand my point, right? So
yes.
from
Yes.
his point of view, like if you allow the unrestricted comprehension, then of course Russell set is a set. Like so, what's the problem on that? But in your work, of course, I understand that Russell set is not a set, right? So,
Yeah.
so what is your view on this?
So I think we don't need the Russell set. I think we can go paraconsistent and still have interesting paraconsistent sets without the Russell set. But I also think that the algebra value model constructions are so wide that we will be able to do this afterwards. To have an iterative paraconsistent set theory where you get the Russell set. Yes, I think in future work this will be possible. Yeah. Yeah. For instance, if you combine maybe if you do it with relevant set theories, I'm thinking their comprehension, for instance, is also defined in a little bit strange way, a more permissive way. So yeah, I don't think this option is completely excluded, but for now I would say we don't need it. Yeah.
Okay. Well, then another question, like what I was thinking that when you actually started the LP valued models, the
Yes.
algebra valued models on the LP algebra, like first of all, you showed that if we are taking the interpretations function, the interpretation function as the interpretation functions we actually took in the Boolean valued models, then many things fails, right? You actually
Yes.
showed that. And then you came up with another interpretation function, which actually you named as IN interpretation function.
Yes.
And you showed that with that interpretation function, actually, the things which are actually failed with the Boolean interpretation function, they actually restored, right? So
Yes.
you showed that. Now, like, what do you think? Like, why it actually happened? Like, what was actually the game playing behind it that this actually happened? Because the LP algebra remains same, that is
Yes.
not changing, right?
Yes.
And then what actually is happening that with the same algebra, that much of difference we are getting in the set theory just by changing the interpretation function. So what was your point? So I actually wanted to know, and then I actually want to draw some conclusion from here. But
Yeah.
first, you come up with your
Yeah,
idea.
I know it's kind of a trick. It's kind of putting two conditions in your language because you have one particular way of interpreting identity, but then still you have your LP condition in the model, right? So I would say this is the trick. You kind of sneak in a second conditional without really putting it there, right? Because this also happens in our models when we do the same trick with the contraposition. We are actually finding a new, stronger stronger conditional which satisfies actually the properties we need, which is a non-contraposing conditional. So I think this is the trick. But we're not really putting in. We just have one conditional in the language of SETI. So we're not doing what Marcelo and for instance Walter are doing, right? So yeah, this is kind of the trick. And it was very nice because in the case of PS3, what was failing was contraposition. So 1 and 1/2 were glued together. In the case of LP, it was the modus ponens case, right? And I don't know if you remember, but first I tried to put like 3 conditions and really fixing each truth value. So for instance, 1 implies half has to be 0. 1 implies 1/2 should not be 1/2, right? And then I found this very simple way of using the less or equal relation.
Right.
And it worked, yeah.
Right. Actually, here what I can mention that since all these things, the totally ordered algebra and the LP is also one total ordered algebra with different implications. But what I can see that, of course, in these algebras, you can use the less than equal to operator in a very nice way, right? If you are going to the other algebras which are not totally ordered, then I think the less than equal to.
Yes, then it's a mess.
Yes.
Exactly. Yes, this is the point. Exactly. It gets a mess. Yeah.
Now, the point is that I was thinking when I was reading your thesis, that actually you see that the previous question that what actually happened that if you are taking the Boolean valued interpretation and IN interpretation on LP valued model, it actually changed a lot. What actually happened? So I was actually thinking this fact that just a second.
Yes.
Yeah. Okay. Yeah. So I was actually thinking the fact that actually when LP was introduced by Graham, he's actually present here. Actually, he had something in his mind, some interpretations, right, about the implication, about the other things, right?
Yeah.
And what I think that whenever we do algebra valued model, the point which actually we miss is that whenever we are taking some algebra, when that algebra was defined, so by the truth tables, actually we can get some interpretations of the algebra, right? That what actually is the essence of that algebra, how by through that algebra we are actually want to see the frame, the logic of that thing, right?
Yeah.
My point is that whenever we are doing algebra valued model with that algebra, but we cannot catch the same interpretation by our interpretation function.
Yes.
Then there is a mismatch, right?
Yes, indeed, yes. Yeah.
The point is here, what I want to mention is that like when Graham actually introduced LP, he had something in his mind, what I think that to see the frame and to see the logic. And the point is that whenever we are trying to see the algebra valued model through the lens of Boolean valued interpretation, it might happen that the interpretation which Graham had in his mind, actually that Boolean valued interpretation is not matched with that one. It also might happen that the IN interpretation also not matched with Graham's interpretation.
Yeah.
But from the mathematical point of view, what we can of course say that, okay, that is of course is a point, but from the mathematical point of view, we are taking the algebra and you see that if we are changing the interpretations like this, with this interpretation we are getting these results, with the other interpretations we are getting some other results. So from the mathematical point of view, of course, like these studies actually are interesting, but I think that what you should think about in future as well, that whenever of course we also, right, that whenever we are working with some algebra valued models, that what the essence of the truth table actually is, whether our interpretation of equality and belongingness actually matching with that.
Yes.
If it is not matching, of course mathematically we can get many results, but whether we are doing justice with the algebra, that we actually do not know. The same point actually goes on heating algebra valued models as well. I don't know that whether the Boolean interpolation function actually gives the correct interpretation to the heating algebra, but of course you can say that, see that all the IGF axioms are valid here. So in your case also you can say that, look, the IN interpolation function validates all the ZF axioms. So that should not be the only only criteria to judge the interpolation function, right?
Yes. Yes.
And
Yes.
So I wanted to make this comment on
Yes.
your study, but of course, like the point which you did not mention in your presentation, that I was thinking then what should be the criteria of checking that the interpolation function is actually like is going to
Yeah.
the close to the interpretation of the algebra. And then in your thesis, I found that this is a comment on your thesis which I liked very much, that actually you worked on this and you found that actually the logic of the set theory on VLP with the LP valued model with the IN interpolation function, the logic of that is the same logic of the LP, right?
Yes. Yes. Exactly. Yes.
So that might be a criteria to check that whether how much we are actually close to the interpretation of the algebra with our set
Yes.
theory, with the interpretation we are giving. So in
Yes.
that case, since till now in the literature we do not have more power in our hand to check that one, only this thing, and through this lens I can say that your work on this on LP valued model is remarkable, because actually at the end you showed that C with the interpolation function the logic actually matches with the logic of the LP algebra. So
Yeah.
so you want to say something on this?
Yes.
Or
Yes. You're very, very right. So this should be the first criteria if the logic matches, and the second one should be extensionality. How much do you have to modify extensionality to make it work? And in the case of LP, you don't. It's just extensionality. This was for me the point where I said, okay, this is a nice interpretation for LP. Because if you apply IN to other algebras, you need to switch
right.
the extensionality axiom. Yeah. So this would be my second criteria. To see how much do you have to modify extensionality. Is this still a... Because it can be classically equivalent, but it... Yeah, you know what I mean.
Yes.
Yes.
Okay, that much was from my side, and I'm very happy to see the thesis, and best of luck, Santiago, for your future works as well.
Thank you.
It's a nice work. It's a nice work.
Thank you, Shuruf.
Thank you. Thank you, Giorgio, for inviting here.
Thank you both for the nice discussion and Sharaf for the questioning. I can now proceed, and now it's the turn of Graham. So thanks again for having accepted the invitation, and the floor is yours.
Okay, thanks, Santiago. I guess my questions are mainly philosophical rather than technical, because technically it's a very nice piece of work. I don't have an issue with that, okay. But I wanted to pick up on the first question that Saurav asked. But let me first of all ask a clarificatory question, because at the beginning of the thesis, and specifically on page 31, you say you're going to compare two sorts of set theory, naive set theory and what you call, where are we? Iterative paraconsistent set theory. And I couldn't actually find a definition of that in your thesis. Can you tell me exactly what it is, please?
An iterative paraconsistent set theory?
Yeah. I mean, you give examples, but you don't give a definition.
Yeah.
I mean, definition of naive set theory is fine.
Yes.
It's a set theory which has naive comprehension and extensionality. What is an iterative paraconsistent set theory?
I would say it's a paraconsistent set theory where the theory axioms are ZF-like. So the mathematical context is given by ZF-like axioms.
Okay, good. All right, thank you. So now I understand what you have in mind, but I want to go back to Saurav's question. and ask about the motivation for your project. Because on the same page, you say you're going to compare these two approaches, and you think that your approach has doesn't face the same kind of philosophical and technical objections that the naive approach does. Okay, and that's what I want to ask about. And of course, what's the philosophical objection will depend on what the philosophical project is.
Yes.
And when I was reading the thesis, I wasn't clear on this, and having listened to your answer to your presentation and to the answer to Saurabh's question, I guess I'm still not clear.
Yes.
So let's try and get this straight. So, I mean, there are so many philosophical projects which might be in this area, right? One is, what's the right set theory? Okay, now that's not your project because you're some kind of pluralist, okay? There's another project, which is the one that's always interested me, of how can a paraconsistent logician who subscribes to naive comprehension recapture classical set theory? Okay. Now that's not really your problem either, because none of the theories that you present, I think, do that. Okay. Okay, I give this sort of model theoretic construction where you can do that, but that's not something that seems to really be central to your focus. So, I mean, there's another question that you might have, which is how, if you've got this paraconsistent set theory, how much actual classical mathematics can you do? Okay, and at one point you indicated that your project was the same as Zach Weber's, and it's not, I don't think, just because he's very much interested in this question when you're using a naive set theory. But he goes out of his way to try and establish all the results of standard set theory in this framework. Now, you never get beyond showing that the axioms of ZF hold in your theory. There's no attempt in your project to see what else in set theory does. So I don't really think that's your project either. Okay, so then there's another project that's in this area, which you seem to endorse sometimes, which is, hey, we want a theory with lots of interesting models. Okay, that's great. But that's not really a project in set theory. That's a project in model theory. And usually set theorists take a wide variety of different models to be a weakness of set theory, just because it shows it's so bloody incomplete. Okay. So sometimes you say that. Okay, sometimes you talk about natural models. Okay, we want a theory with natural models. Well, okay, what's a natural model? I mean, that's not at all obvious. What's natural is often the eye of the beholder. But sort of coming back to your comparison with your approach and the model theoretic approach, the model theoretic approach has lots of models. Okay, that's great. If you're a model theorist, some of them are interesting, some of them are not. Well, that's life. Some of them are very natural. You know, there's essentially the cumulative hierarchy, and then all this inconsistent, strange stuff sitting up top. That's natural in a very interesting sense. So it's not clear that if you demand naturalness, your approach is better, just because of this sort of inclarity of the notion of naturalist. So I'm sorry, that's a rather long preamble, but what I wanted you to do was just sort of focus on what exactly is your project, so we can think about that in more detail.
Yeah. So I guess you're right. It's a model theoretic approach. The goal is model theoretic. Yes. Yeah, this is true. But I always assumed that if you have more models, you can do more forcing and also more set theory tools. I don't think that it's necessarily maybe better than the naive approach, but I have noticed a certain tension in the naive approach, which is kind of, it has to be classical, but at the same time non-classical. And I think in the iterative approach, this is resolved a little bit better. I think this is maybe the only advantage. Yeah, because...
Okay. What are you looking for Are you looking for plurality of models, or are you looking for models that are natural? These are not the same thing.
Oh, okay.
You might have very few models which are all natural, so they're not the same thing.
So I would consider any model network if it's in a cumulative hierarchy. So all the models that we look at are natural, I think.
Well,
Because,
I mean, is that true? I mean, you have the axioms of the cumulative hierarchy, but you don't have all the properties of the cumulative hierarchy. At least you don't show that. So,
yes.
in what sense are they? I mean, in what sense are they? I mean, you have no guarantee they're natural in your sense.
Yes. But I mean, what do you really want about iterative conception, right? You want that your axioms hold, that, and I mean, what else would you like?
Well, you want the cumulative hierarchy with its usual properties.
Yes. And I think we precisely get this. So also George Schuler, we wrote a paper called Ideal Elements for Set Theory, where we precisely argue that this is the case, that you get the standard properties of the cumulative hierarchy.
Okay.
Yes.
So in any of your theories, can you prove the standard properties of cardinals and ordinals in your models?
Yes.
Okay. I didn't see that in your thesis, right?
Yes.
Okay.
Yeah. Sorry. Yeah.
So that's important. All right.
So yeah, just a clarification. I don't know if for every model it holds, but for all the totally ordered models, the models we saw first, it holds. This was shown by Shurov now recently, but unfortunately, the paper was not published until now, so I didn't include it. I will include this. Yeah.
Okay, that's good. I mean, that puts you closer on the page to Zach's motivation, because
Yes.
I mean, he really did want to show that you could do kind of standard set theory in his theory.
Yes, exactly.
Okay, so I mean, if you can prove, well, let me ask you a question about that.
Yes.
Do you get presumably? Okay, question. How much of the theorems of ZFC do you get in your models?
So I think in the one where you have model spondents, you get everything. Yes. Yeah. So if something holds in the ground model, it will also hold in the algebra valued model. I think it goes like this.
Okay.
Yes.
So those models are also extensions of ZFC in a sense. Like
Yes.
Yeah. Okay.
Yes.
So
Yes.
I mean, if we're comparing like with like, I mean, a fair comparison might be those models with, say, the collapse models of ZF that I construct.
Okay. Yes, precisely. Yes.
Yeah. That would be an interesting comparison, I think.
Yes.
Yeah. Let's leave that subject. That's good. Let me ask. I mean, I have several questions. I'll just ask one more, and then I know other people want to ask questions. So when you're evaluating the model theoretic construction, you have a number of points. The one I really didn't understand was the one about having to presuppose that ZF is consistent.
Oh yeah.
And I wasn't aware of Incavati's book until your thesis, so I went back and I dug that out and read some of it. So that was interesting. Thank you very much. And that's one of his objections, right?
Yes.
And I didn't understand it when he did it either. So my question for you is, why is it a problem if that approach presupposes the consistency of ZF?
I mean, because intuitively, if you suppose it, then this is against the assumption that I mean, you don't accept the cumulative hierarchy as the intuitive representation of the universe of sets, right?
Well, yeah, I mean, it's part of it, but not all of it.
Yes, right. Then this is the first argument, I would say.
But what's that got to do with the consistency of ZF?
I mean, you would say one of the reasons would say, okay, assume ZF is consistent.
Well, everybody. Okay. But okay. Sorry, I interrupted you.
Yes.
Please.
No, please.
No. I shouldn't have interrupted. I should let you finish. Please carry on.
No. I mean, if you say that ZF is consistent because your axiom holds, because they are true in your model, then you have this problem of separation, right? And if you say that ZF is consistent because the cumulative hierarchy is our intuitive representation of sets, then this goes kind of against the diagonalist.
Well, hang on. Look, the consistency of ZF is not the same as the cumulative hierarchy. I mean,
Okay. Yes.
Most mathematicians will think that ZF is consistent, and I think ZF is consistent, right? Do I think that the cumulative hierarchy is a consistent structure? That's different, because of course there might be more to cumulative hierarchy than you can prove in ZF. But even then, I guess that I think that the cumulative hierarchy is a consistent structure. It's just that it's got inconsistent stuff outside that. Okay. So it doesn't seem to me that it's a problem either if I assume that ZF is consistent, which everyone assumes, including you. Okay.
Yes.
Or even if I assume that the cumulative hierarchy is consistent. Well, so I just didn't understand the Incavati objection.
Yes, you're right. So yes, you're right. I always thought it's kind of the same as you said, ZF is consistent, the cumulative hierarchy is consistent. So I just took the argument. But you're right. If they are different, if these are two different topics, then yes, then this should not be the objection. Yeah, you're right.
Yeah. I mean, that was the kind of the main objection in Incavati that I found puzzling. I mean, the others are mainly things that we know about already, and I don't find terribly worrying. But but you know, that's just a comment about me, not about your thesis, so it's irrelevant. Yeah. Okay. Look, I've got several other questions, but let me hand the chair back to Georgie. Maybe we'll go around again. Maybe we won't. It's up to him.
Thank you, Graham.
Thank you very much again for the nice discussion. So we can go on. I mean, as we were saying before, remember, if you want to jump in some other discussion, or you want to take over some of the points that have been discussed, again, just feel free to do it. So we are here to discuss Santiago's work. So we continue in the order we set of distance. So next one will be Rodrigo, since he's in Brasilia. And so thank you very much, Rodrigo, again, for accepting the invitation. The floor is yours.
Thanks, Giorgio. Thanks, Santiago. Santiago, I appreciate very much your work and also your presentation. I would like to say that you were very good presenting your stuff, very calm and precise. So I would like to make this point before the questions. Now, let me say that something caused me a little bit of trouble in your thesis is that you set a general algebraic apparatus, right? And then you focus on this totally ordered structures, which somewhat trivialize the algebraic structure, right? Yes. The mid and join are just minimum and maximum. Negation is also somewhat trivialized, either 0 or 1. And in fact, you make this point in lemma 4.4.3, where you describe negation, implication, and the algebraic structure is very simple, right? It is very straightforwardly defined from the total ordering. And so this caused me some trouble. For example, right on page 21, when you say that the positive, right, is an ultra filter or a filter, just page 21, just before section 2.3. So positive and negative are not filter and ideal in a general lattice, right? This is the positive elements.
Yeah.
The set of positive elements is not a filter in general. So that is this mix, but it is a filter in your case because you are dealing
Yes.
with totally ordered structures.
Yes.
So there is a mix between a general algebraic apparatus and the particular cases that you study that are somewhat much more simple. And so
Yes.
I wonder if that is a good option for your presentation because it sounds like you set a general theory of, don't know, topological vector space is locally convex, and then you focus on the real line. It is, so I am exaggerating the point just
Yes. I
to
see.
try to communicate the strangeness that it caused to me. So um, also the negative elements are not ideal, and that is one point. Uh, a second point that I would like to make is that I have also no technical problems with your thesis. There is one lemma that I have not followed, the lemma 3.7.13, but that's not an important lemma, I think, in your thesis. It's some digression. The statement already has a problem, and it is in chapter 3, 3.7.13. It is about NF and the cost approach.
Oh yeah. Right. Right.
Well, you said you want to show that, and then it comes this formula. At the end of the formula, there is a problem. There is y such that there is something missing here. X, y, what? There is y such that x, y, something. And,
Right.
and I think the proof, I have not followed the proof. Uh, your strategy seems to show that the usual way to define the set through comprehension cannot work, but well, I don't understand why this proves that there is no other definition, for example.
Yes. Of course. Yes. I see.
I have
So
some problem with this. There are some typos, some I will not go into this. And then I would like to focus on also on the philosophical project that you have here, right? Uh, uh, just before that, uh, you have mentioned also that you have generalized the heighting approach, etc. But then this is not quite correct because your structures are totally ordered, and usually in the Boolean valued models, the Boolean algebras are not totally ordered,
yes.
right? They are
It's
far from being totally ordered.
yes.
So your class of algebras is not bigger than the class of Boolean algebras. It is a different class of algebras.
Yes.
So it is not quite a generalization in the usual way. You have used the word generalize in page 96, section 4.4.2. Well, but then to the philosophical project. Your project, as I have understood, is a model theoretic project with no clear axiomatic correlate.
Yes.
This is very interesting to me, but it makes me question what is the appropriate notion of equivalence between models. You have defined this epsilon elementary equivalence between models, or non-epsilon elementary equivalence. But in this definition, it seems that one model can be inequivalent to itself depending on what filters you choose. So if you take one model with the filter that is just 1, and another model the same model with the filter 1 and 1/2, I see no reason why these two models will be elementary equivalent. I think that they can be non-equivalent according to your definition. So the same model can be non-equivalent to itself. So when you don't have the axiomatic correlate, we somewhat lose the comparison between models. And you have set this comparison, but I am wondering if there is another comparison, or even the notion of homomorphism between models can be non-standard in this case, or even isomorphism. What is the symmetry of the models? Right? It is well. So I have been talking too much. I don't know if you want to remark something.
Thank you very much, Rodrigo. So just one point. You are bothered by the fact that for instance, if I take 1 on as a filter, or 1 and 1/2, that they are different models, because there will be different models, right? You have really different sentences which will be validated by these models.
Yeah, but your definition is on page.
So you want to include this case?
No, but that definition.
I think
Yes, your definition makes this point that you have. I don't know where's the definition right now. Let me find it.
Let me also find it.
So, your definition says that two models are non-elementary equivalent with respect to filters. Yes, it is given at page 31.
Yes, exactly.
We say that VA1 and VA2 are non-epsilon elementary equivalent. Then with respect to a filter F1 and a filter F2, if this holds.
Yes.
But notice that using your phrasing, we can have VA1 and VA1 non-elementary equivalent with respect to F1 and F2.
Right, but this is good, right? Because I mean, I always
the
thought
model you are thinking of the model as the model together with the filter.
Yes, exactly. This is yes, exactly. Yes.
So your model is the model together with the filter.
Yes. Yeah. But what you said about homomorphisms, if you can, maybe not right now, but afterwards we can talk about this, and because this
because of your homomorphisms, must take into account the filters then,
Okay.
because the model comes
Yes.
together with the filter. So, well, that's the general point on the comparison between models, because you don't have an axiomatic correlate. So you don't have a theory to say that, well, they have the same theory.
Yeah.
There is no robust notion of a theory of the model here, because there is no underlying logic that is shared by the model.
Yeah. Yeah, we still have to look at this and really find, as you said, the axiomatic counterpart. Yes, this is true.
Yeah. And well, I think it is an interesting point to put the model theoretic project forward, because the tradition in the foundations of mathematics is axiomatic, right? It's proof theory, right? Hilbert, Frege tradition is Beweis theory, proof theory, right? Foundations of mathematics is to find appropriate axioms and to derive the theorems from the axioms. And the model theoretic approach is somewhat different, right? The point of the foundations is to clarify the mathematical notions, and you do that by exploring the models, because mathematical notions are embodied in the models, or are represented by models somewhat. So that can be a thesis or not. Right? And so I appreciate that kind of project, right? Well, there are some slight mistakes that I have found, but I will not bother you with that. So thank you very much, and I really appreciate your work.
Thank you. Thank you, Rodrigo. And I will try to phrase maybe the introduction differently, to doesn't make it too general. Because afterwards, after I wrote everything, or after most of it was written, we actually found a lot of models which are more general, which are not necessarily well ordered, and which can branch. But yeah, I know. I will try to phrase this differently. Yes. Thank you.
Thank you very much again, Rodrigo and Santiago. So,
Giorgio,
Shraf, you say something?
Yes.
Yeah, please go ahead.
So actually, before going to the next question session, so I just want to add one thing on the question of Rodrigo, that the model what Santiago took, you said that the model with the filter he took, right? What I think that in the classical case also do the same thing. The only difference is that since there the filter is only singleton 1, we actually do not write it.
Yes.
But if you are violating from that point, then actually you are considering, my point is that actually we are considering models with the filter. So always. So what is reflected here in his case? But it's a good point to mention.
Unless Rodrigo wants to add something else,
No, that's okay.
we can go on. So we have the fourth member of the committee. Again, thanks, Katerina, for accepting the invitation. And now the floor is yours, who's directly from Campinas.
Yes, thank you very much for inviting me and giving a chance to read this thesis. I should confess that set theory is not my main area of specialization, so maybe I will be more philosophical, more even naive with my questions. The thesis is well structured and very easy to follow. This I really appreciate it. I didn't spot any technical inconsistencies, but I have some stylish and philosophical remarks.
Yes.
So first one of the main worries concerns the general philosophical motivation. So you start already the introduction, page 16, with the following phrase, that in this thesis we try to convince the reader that there exist very simple methods for constructing models for non-classical set theories, and that these models might enrich our perspective of the pluriverse of sets. So already here I have the first remark about this pluriverse of sets. This discussion, okay, here I maybe also will be a little bit too much judgy because I'm not familiar with Brazilian thesis, how it is usual here, more with French, which aims to be self-contained, sometimes too much. So I've been a little bit unsatisfied with the fact that this conception was not so much present. So I found a little short discussion only in the conclusion on pages 176-77. And my main question there is, does it really the fact that pluriverse conception can be realized not only on classical models, but as you show also on non-classical, paraconsistent, paracomplete something, does it entails real difference, conceptual difference for the pluriverse conception by itself, that we are really augmenting with others?
Yeah.
So this is,
Yeah.
look,
Should I answer or should I wait?
as you prefer directly. If not, I can go with other questions, as you prefer.
Okay, if I just can make two small remarks.
Mm-hmm.
Of course, you're right. It should be self-contained. I will fix this in the introduction. Yes.
Mm-hmm.
And I'm not sure if it has a deep point in the philosophy of mathematics. I think it's interesting to notice that ZFC can be realized by non-classical set theories, but I think this has been shown also before. So I'm not 100% sure if this is really a novelty. But the fact that you argue that the iterative conception is not necessarily classical, I think this is an interesting point. Yes.
Mm-hmm.
Yeah.
Okay. So then, still on the same page, you mentioned this, what it is called, no natural model objection, which I also seem to be too short. I would like to find some quotations, some literature on this, because these aspects, I appreciated the technicality, but there is missing discussion behind, because yes, as Graham also said, what is natural in this case, why we need exactly this conception. I see your point, but I had to guess myself. This is a little bit, yes. So, yes, and another point that, again, I'm not very much set theorist, I'm not very much paraconsistent. I sympathize with both fields, but I found some missing motivations for considering models for paraconsistent set theory in the first place. So you've exposed the naive set theory and explained the problems with it. Then you've introduced the iterative conception. And then what I'm missing is the passage, how we go to the paraconsistency. So even in today's presentation, you've asked a question like, if we ask researcher, why don't you work in a non-classical framework? Your answer are that researcher, because I don't have it. But from my perspective, the researcher would ask, but why should I work in non-classical? Why should I work in paraconsistent? So this passage a little bit leaves me.
Yes. Yeah, I think I have no direct answer for this, because the focus on paraconsistency was at the beginning mainly motivated because in Campinas almost everybody does paraconsistency.
Yeah, but to make this choice consciously, in the sense, why?
Yeah, I know. Well, I would say it's interesting because it's a limit case. So paraconsistent logics are only considered very strange logics in a certain way. So you can really say that if it works in paraconsistent set theory, then it's great, right? So I think this is one point. And I think you can go non-classical as you want to go. So paraconsistency was just the case that we had already Shurov's model, and then we want to see if we can build it up. But at the end, the project would be to extend it to every non-classical logic. Yes. There is nothing very, very special about paraconsistency. Yes. This is how it. But you're right. I have no true motivation or like very deep motivation. I don't think that reality is paraconsistent. I don't think, or that the theory that we use to describe the world is paraconsistent. Or I'm not a dialectist. No.
Okay.
Yeah.
Okay.
So
Yes.
Can I briefly come in on this before you carry on, Katerina?
Yes.
This is a very good question. Okay. I think, if you believe in naive set theory, there's a very simple answer, namely, the naive abstraction principle seems to be true. So there is a reason for investigating set theories which accept it. Okay. Now, obviously, Santiago cannot go that way. I think he has an answer to your question, but it goes via pluralism. So if you think there's uniquely right set theory, then we have to argue about what it is. Okay, but suppose you think that there's a plurality of universes, the sort of view that Joel Hampkins has, then there's a question: why should the universes have different and interesting structures? Why should you restrict yourself to universes which have an internal logic of classical logic? If you think there's something privileged about classical logic, well, maybe there's an answer to that. But mathematically speaking, it's hard to see that there's a privilege to classical logic. And if you take that view, then you might say, well, let's consider all the other universes that are out there with internal logics which are not classical. And I would have guessed that that's the sort of way that Santiago will go, but I'll let him speak for himself.
Yeah, no, exactly. Yes. Yeah, probably that's the best answer. Yeah.
Okay, I see the point here. Okay. Thanks for this. Yes, there are some other comments, but I try. Okay, it is a little remark. I'm not sure. I'm not sure about your criticism of American-Australian plans. But you say that they fall short in capturing certain aspects of negation. I don't follow why whenever an operator. So I like the distinction you've made for Australian plan for an operator to be satisfying the Australian plan, but I don't see why whenever an operator satisfies or not each of plan or each formulation, this leads a conclusion to the fact that the plan falls apart, because they have their own definitions of negations and not yours by itself.
Yeah. So I would say the problem with the Australian plan is then you can have logics. Take, for instance, linear logic, pre-value linear logic, and priest logic. They are the same, but you have a different filter, right? And then suddenly in one you have negation, and the one you don't have negation, right? And this is what have been also criticized from the side of the Americans. And in the case of the American plan, they also don't really say what they want. I mean, they are also like a little bit,
But there, honestly, I have a feeling that Cleanest negation and Priest's negation, even though the truth tables technically are the same, but it is not the same negation, just because of the designated, anti-designated values doesn't behave the same way. So this is.
But it's strange because from an inference engine's perspective, it is strange, I think. Yeah. But you're right. Technically, it's they are also different. Yeah. Because for one contraposition holds, for the other one not.
And also about negation. This is one of the crucial points for me. So on page 132, you write that operators, okay, for negation star E and star C are intuitionistic-like negations. Also in the presentation, you've again repeated this sort of definition. But I find it very confusing, to be honest. Why? First of all, you are speaking about many valid operators, which is totally against the whole idea of intuitionistic negation, intuitionism by itself, from Gödel's results of 1932. Secondly, yes. I don't know if you want for this part reply straightforward.
I was looking it up.
Yes, page 132. It is like a conclusion of the chapter. I remember. Yes. So first of all, I don't like exactly why you are calling these negations intuitionistic. First, again, because of its many validness character, and it seems not to go in line with intuitionism by itself. Secondly, you take these negations as primitive ones, and in intuitionism, they are definables. They are defined with implication and bottom already. It doesn't match.
Yeah. Yes. So the name is more arbitrary in this sense. But if you consider three-valued algebra and you consider the three-valued Hating algebra, then this will happen actually. The negation will behave in this way, that it's not cyclical and it doesn't cover uniformly the space of negations. So actually it does kind of capture the intuitionistic negation in a certain way. Yes.
Okay, on Hating, no, I see that it is related to Hating algebra, but there you should be more attentive.
Yes.
I would not advise to use intuitionistic because there is famous works, works on the criterion of intuitionism. And
yes, you're completely right. This is true.
Yes. So yes, and another probably yes. Probably last, curiosity and just interesting for me. So you cite on page 24 validity, which is defined as truth preserving. Later you speak about falsity preserving and even ordering, if I remember well. Are you familiar with the work of Cabrera, Segre, Ripley, and Van Rouge, where on strict tolerant things?
Yes.
So you know these ST relations which are preserving.
I was always against it because the failure of transitivity, but yes,
this was my question exactly. Did you consider by itself to use these types, and do you think it might give? Partially, you already said that no, but
no. This is true. Yes. This is definitely in the future. We should try this at least. Yes.
Yes.
T-logics,
Yes, but the other comments I don't insist. So thank you very much for this thesis again. Congratulations for this.
Thank you very much. I hope that I made remarks on all the comments.
Yes.
So I think I missed something.
No, I think I'm satisfied. Thanks.
Okay. Thank you.
So thanks again for the discussion. As you some of you may know, the thesis of Santiago was also co-directed by Rodolfo, who's our algebraic guy in some sense, exactly because it was on algebraic models for set theory. And so Rodolfo was very valuable in insights on the algebraic part of the work. As by the rules, Rodolfo is not officially a member of the committee because the rule goes that only one person should be in the committee. But I'm happy to give you the word if you want to add something, if you want to comment on something. Just knowing that it's a friendly comment from from the audience, even though it's clearly not. So, please.
Okay. Can you hear me?
Yes.
Yes. Okay. Well, thank you, Giorgio, for the invitation, for being here, and thank you, Santiago, for your presentation. I just want to say a couple of things regarding Rodrigo's remarks. The first is initially, because he said that why do we have such a general algebraic structure when in the end everything will be decided in a poset. I mean, total poset, totally ordered. Initially, the idea was to find, set a general situation so you could see what to find there. But then it got shrinking because it didn't work. So in the end, it was just this totally ordered poset. Of course, I didn't like that, but the idea initially was to see whether you can find a more general situation. So maybe this is, in the writing, we just kept the same language, but that was the reason. And well, regarding your point on ideals or filters, I don't remember the page, you mentioned something. I remember saying something regarding that. I don't know, I'm not sure whether Santiago introduced this correction. In any case, we were making the reading, correcting the writing. And for some personal reasons, we had to stop on page 45 or something. But the idea was to complete the corrections of the writing. That's all I want to say, really. Thanks again.
Thank you, Rodolfo. Just a couple of comments. First, on the in some sense, the criticism that these algebraic structure are simple in their definition. We actually managed to extend this result with Sharaf and Santiago to a larger class of algebras, which are as complex as Boolean algebras, for example. So you get many different algebras for which you can actually build these algebraic models. But in some sense, it's also not very satisfying, and because again, the ultrafilters you can define there are just and just a singleton, just one ultrafilter, because they have a coatom. So the point is, I think that the criticism still stands, but it's I think that the point is about, and this is an important point that should be developed later, on the complexity of the stone space associated with these algebras, that for now are very simple because they're just trivial, and this is what, as also Rodolfo was saying, this is actually what made all these results possible. But of course, there's many different ways in which this can be generalized, and I'm confident that some more interesting examples can actually be given. And this would actually make possible also to define a forcing relation similar to the one we have for Boolean valued models. So where you actually need some variation between the ultrafilter you can choose, and this is kind of the essence of the forcing relation. So that was just a very general comment. That also it was a way to say that, I mean, this work is still ongoing. We are finding some very nice results. And I just wanted to comment before asking everybody if you have some last remark on the general goal and the project of the thesis. Also because, I mean, a PhD thesis is always the result of different opinions, different directions. And in this case, it was also a choral work, exactly because, I mean, Rodolfo was important in the development of also Schraff. And I can, about the general goal of the project, which I think, I mean, technically very interesting, is something that is similar to what Graham was discussing in the case of Hamkin's perspective on the topic. And I think that there is a way to look at this work also from a classical point of view, which I mean, it was mine when I started this work. Which is exactly to show how hard it is to make an argument that CFC is intrinsically classical. Exactly because all these models actually give examples of very well-behaved models of CF, where you can develop a lot of theory, of set theory, as we know it, as the theory of cardinal numbers, but in which the underlying logic is classical, so non-classical. So from a classical perspective, it put pressure on explaining why we use classical logic. And an important step in this direction is something that we are planning to work on, which is exactly starting from these models, which are non-classical, try to build the classical ones using Bohlenfeld construction. So that, in the sense, all this work has been done with the classical meta theory, where we have V behind us, where we actually do these constructions. And this is a classical environment where we can actually build non-classical models. But if it's also possible to show that from this non-classical world, universes, you can actually build the classical ones, well, this would put actually even more pressure on the unicity perspective on classical logic in the foundation of mathematics, because you would be actually able to mimic all you can do in the classical case from a non-classical perspective. And this would actually be philosophically interesting, although mathematically challenging. So that was just a very general comment on at least my perspective on the project. But of course, Santiago was, since the very beginning, interested also, and also Schraff, from the non-classical and the part-consistent perspective of building part-consistent models of set theory with such very nice properties. And I think that the discussion was very interesting, what we had today, and it shows that some work still needs to be done in understanding what is the relevance of this model from a purely consistent perspective. But I mean, I think it's also part of the work to not to solve and close any problem that comes out of a PhD thesis. So that was just a very general comment on the discussion. If any of you want to also add something, or Santiago, feel free to do it.
Well, can I ask Santiago about his view about what you just said? Because I find it interesting. I mean, if you talk to classical logicians about non-classical logic, the first thing they'll always say is, yeah, but you use classical logic in your meta theory, so you're committed to it. Okay, that's always the first line. And it's certainly true that, for the most part, one can think of a meta theory as regimented in ZF. Of course, meta theory is done in a set theory, so normally one thinks of it as done in classical ZF. All right. So what is a non-classical logician to say about this? Well, they'd say, I think, exactly what you said, Giorgio. Look, if you're engaged in a project of showing how power-consistent logic can recapture classical ZF, then the obvious reply is, well, anything you can do classically, we can do as well. So it doesn't privilege classical ZF, because we can show how to do things in classical ZF. But then the reply usually comes back, yeah, but okay, you're really presupposing ZF, that's where you're starting from. You're kind of bootstrapping, but you're bootstrapping from a ZF position. That's the reply. I'm not saying that it's a good reply, but it's a standard reply. And my question for Santiago is, what do you make of this reply?
I would say it's not about this assumption. It's about managing to get the model, right? So similarly, as you argue, it's not the name of the game to see what's the first assumption there, but it's really about getting the model and showing that it is possible. Yeah, rather than this would be my answer. Yeah.
So when you get it, don't you presuppose the correctness of classical logic, or at least classical ZF?
Yeah, but I mean, who cares? I mean, yes, I think there's a commitment that we have to do. Yes. Yeah.
But then doesn't that show that your non-classical members of the pluriverse are kind of pathological in some sense?
I mean, in the case of our models, it's interesting because they all live in the same universe, right? I mean, you have Boolean valued models and you have these non-classical models, and they have all the same ontological status. So yes, I don't know if you can call them pathological, right? Because from the perspective of the algebra, it's just the same. It's just functions. Yeah. But yeah, I would always say that but I get your point. Yes, it's. Yeah.
Well, I mean, I wouldn't be as conservative as you are, but if you are conservative in that way, I rather suspect you're giving the sort of orthodox view. You're conceding a lot to the classical view.
Yes, I guess yes. Yeah. Yes, in a certain way, yes. Yeah. I don't know. Do you have a better answer for this argument?
Well, I'd say, look, the fact that we can show paraconsistently how you can capture all of ZF, theorems and all, shows that anything that you think you need classical logic for, you can do with a paraconsistent logic. So there's nothing privileged about classical logic. And if your results are proved in classical ZF, well, okay, sure. I've shown you how to do that paraconsistently. What's the problem? So,
yes.
I wouldn't be as conservative as you, okay?
Yes, okay, I see what you mean. Yeah. No, I guess I would go in between the same lines, but still I mean, we are working in a classical method theory. But no, I guess you're right. I would also go kind of between these lines of saying that we are working in classical method theory, but still we can do everything you can do, and we can make some more sense from a paraconsistent perspective of.
Well, I mean, you're working in ZF.
Yeah.
Okay. But the very thought that this is essentially classical is not true. And that's the point that either you made or Giorgio made a moment ago. I forget which of you it was. You can, I mean, in a certain sense, you're showing how you can use ZF without being committed to it's being based on classical logic.
Yeah, definitely.
Shraf had the hand raised.
Yeah, so first of all, I don't know that whether I have understood the problem clearly, because my internet is like not working properly. So many times I'm out and I cannot hear you properly. But anyway, what I have understood as an answer of Graham's question, that getting all the axioms as valid, all the ZF axioms as valid, doesn't actually mean in these cases that actually you are getting all the theories of the classical set theory. So that's the point. Like, of course, it's true that we are showing that if you are considering the ZF axioms as reasonable axioms in some philosophical sense, then in that case, we if you consider our point of views, like we actually prefer that the ZF axioms, we can see the ZF axioms as in some sense that they are reasonable, But of course, in the same time, we believe that there should be some modifications in the classical logic axioms as well. The motivations of the paraconsistent logic from where we got. So what to do in that case? So in one hand, we see that the ZF axioms are reasonable. In the other hand, we see these things, the logical perspective. So now we want to come up with something which actually make the ZF axioms valid, keeping the logic paraconsistent in that way. But of course, it's true that it doesn't mean that all the theory, whatever we are actually getting, whenever we are making all the ZF axioms valid, are actually same as the classical theory. So it's actually not that. That's the point. So whenever we are saying that ZF is classical, like by making the validity of all the actions of ZF, if we consider this thing is classical, it's not true. We have already proved it, right? That it definitely is the case that there are very much non-classical algebra valued models where all the actions of ZF are true.
That's absolutely right. Okay, the
Yes.
fact that you've got all the axioms doesn't mean you've got all the theorems. That's why I was pressing Santiago about the question of whether there are models that he's constructing where you get not just the axioms but also all the theorems, because I mean you need that if you're going to run the kind of line that I was running just now.
Yeah. True. Yes. So as Santiago was also mentioned at some point, like I just want to add one or two lines on this, that what was our motivation when we discussed, like Santiago, Giorgio, me, that the point is that you see that I always took the project like this. Our daily life mathematics, the daily life mathematics is only like whenever we are going to the market and doing things, like we are just adding things, subtracting things, and if you extend it, and then you will get some differential equations integration, which we are actually using in the modern science. But of course, those things are also like a generalization of addition and multiplication. We all know that, right? So the way we defined the differentiation and everything, they are just the modifications of all those addition and multiplication, all these things. But the point is that in the classical mathematics, they only do not deal with these things. Whenever you are considering, suppose, algebraic topology, you can show some practical practical applications of algebraic topology, but it's not the case that algebraic topology is needed to understand the world. So at least whenever it was built, it was not the motivation was not like that. So the point is, if we can make mathematics which actually agree upon the daily life needs, right? That the daily life mathematics, like the addition, multiplication, and all these basic cardinal stuffs, but then they disagree with the other abstract stuffs with the classical one, then why to take the classical mathematics only? Why not to consider the other possibilities as well? So that was actually the motivation, and the motivation of behind all these works what we are doing. So as a answer of your question, which you started with, that what actually is the motivation? So probably that is the motivation. Like as you also said at one point, that why to only from this pluralism view, why to take only the classical one, right? But yes, like what I can see, that whatever we need, that every day, the from the nature, what the minimum mathematics we actually need, if that is satisfied in some other theory, but then it differs in the abstract level with the classical one, why not to take the other thing? Why to take only the classical one? Probably that is the motivation. And probably for making all those basic mathematics same, probably you need the ZF axioms, and probably that is the reason that why we always wanted to make the ZF axioms valid. And we don't know, it might happen that without making all the ZF axioms valid, you can get the basic mathematics same. It might happen, but yeah. So at least we are getting few models where ZF axioms are valid and also the basic things are also valid. Yeah, that was my point to make here.
Just a comment in what we've been discussing. I think there's different perspectives that arise, and a distinction that Rodrigo was making earlier on more proof theoretic Hilbertian view on the foundation of mathematics is what one can use to just say, well, you have a power consistency F, you don't really need to care about the meta theory where you build all these theories. While there is the more model theoretic one, which where of course it is important to understand exactly also where you are trying to build your foundation of mathematics. But in both cases, I think that if it's possible actually to show that you can actually do mathematics and the foundation of mathematics in both senses with a classical and non-classical perspective, I think that there is an important philosophical question that arises that is something in the vicinity of an indeterminacy problem of what our theories are about. That it's unclear, and it's not only about this competition between classicality and non-classicality, but it's about not knowing what in the end is theoretically the one we should use. But then, as actually in the case of Putnam problem, you get a Quinean perspective where you actually need some practical reason for doing this, and on a practical ground, then the discussion is very much open. But yeah, just a comment out of the discussion. So if you don't have any other question or suggestion or comment, I think we can end here the defense. So what happens now is that we separately deliberate on the outcome of the defense. And Santiago, and I'm sorry, but also Rodolfo, you should probably leave, but you can come back after that. So there are two ways of doing this. We can either stay here, but you have to interrupt the recording, or we can create a new room, and we the five of us can go there. Santiago, you probably know if at least if the first possibility is really possible.
I'm not sure if it remains open if I close it.
Okay.
So,
So I can send you a link where we can with a new room where we can go. We can just switch off the microphone and the camera, and we can all go there. So that actually you guys can actually stay here. Oh, too late for Rodolfo. Okay, I'll send you the link. I've just sent it there. So see you there, guys, in a moment. Santiago, are you there? Apparently not. Let me write him an email.
Yes, yes.
Okay.
I'm sorry. I switched the t-shirt because I was sweating. Yeah.
Well, the tension of the defense. So, I mean, we delivered and the thesis is approved. So you are officially a PhD now. So congratulations. It was the discussion was very interesting, and we'll also send you also an evaluation, big evaluation of the work after collecting all the signatures. So again, I would like to thank everybody for having participated to this and for the very nice discussion. And congratulations, Santiago, to you.
Thank you very much.
Yeah, congratulations, Santiago. Well done. Excellent.
Thank you very much.
Congrats.
Congrats, Santiago. Congrats.
Thank you, Shura.
Congratulations.
Thank you, Rodrigo. Thank you very much.
So, I mean, our work is done. Again, Santiago, thank you very much, and everybody for the very nice hours spent together discussing Santiago's work. I'll then circulate very soon all the details so that you can take care of this too. And again, thanks a lot, and see you next time.
Thank you, Giorgio.
Thank you.
Yeah. Good night, everybody.
Good night, and have a nice day.
Bye-bye. Bye-bye.
Bye.
That's it.